Hello everybody, I am Turjashu. I'm back with my tutorial classes, and as I had told you before that I'll be covering my next session on basic clock module that's called BSCTL, that's the control register, or you can say BCM. It's called Basic Clock Module Plus. That is, it provides the entire clocking facility to the microcontroller. And if you look in my previous session of my tutorial of this particular microcontroller, MSP430 X2XX series, then you must have seen that I have explained the architecture of the microcontroller. And what is more important is that before we move on to the various details of this particular controller, and we move on to a project that we have promised to be completed, we must understand the basic units that are required to power on and run this kind of microcontroller. So the very basic thing on which a microcontroller will always rely on is the clocking module, because it's a synchronized machine. It's a clock synchronized machine, right? You supply you supply a pulse or a square wave or any kind of clocking, your device will work. If you don't, it doesn't. It's as simple as that. So when you halt the clock or you halt the oscillator, your processor goes to a halt. So you must know how the clocking functions, how the basic clocking functions inside the MSP430 2XX series, and this entire chapter is totally about that thing. Uh, well, the video is a bit boring, I hope so, for many of you, because I will just go through the data sheet. But promise you, one thing I can promise you is that I won't go into much details, because that's your part of the job, your work that you have to do. You will have to study a bit and see what more details are given. I will just explain some basic parts of the basic clock plus module. Okay, so let us start from here. Now I hope by now you have downloaded this particular uh, data sheet, that is SLAU 144I, that is the 2012 version. So if you haven't, then you can follow the link in my last class. Over there I provided the link. You should download this datasheet. It is very important for any X2XX series microcontroller that is manufactured by Texas Instruments, and it's very handy. You don't have to go through the entire of the datasheet, but you must know all the kind of basic functions that are done, because the basic functions are very important for the microcontroller to power up and run simple programs that are already given, either inside the Resource Explorer or in the Code Composer Studio, or maybe your own program. So we can see that this entire chapter has three parts. There's introduction, operation, and registers. So the most important part is, obviously, for the programmers, is the registers, right? So the registers is where you can really configure. So for the registers part, I'll go on later on. The first thing I must tell you is the introduction. So let us go directly to the introduction page. See, as I told you, this basic clocking system has mainly, you can say, three sources of clock, right? One is the ACLK, as you can see over here. I will just make it a bit bigger for you to understand. One is ACLK, that is called the auxiliary clock. The auxiliary clock is used to provide clocking to various parts of the microcontroller when the microcontroller is in deep sleep mode, that is in the low power mode. Then there is MCLK, that is the memory clock or the main clock or the main system clock, this MCLK can be used for the peripherals as well as the core. So it is up to you whether you configure in the registers that I will show below, that whether you want to use the MCLK or the main system clock for the core only, or for the core as well as the peripherals. But make sure if you're using the MCLK for the core as well as the peripherals, then you have to use some kind of methodology, so that you know, your peripheral works as fast as a core, because the core can be, you know, geared up at around say 1 megahertz or maybe say 12 megahertz. And if your peripheral, if say for example your I2C peripheral, that is a serial communication peripheral, if the serial communication peripheral doesn't work at such high speed, then I'm sorry to say your high speed clocking of the peripheral is of no use. You're basically wasting the clocking. My suggestion would be to keep the MCLK extensively for the main CPU and maybe some vital functions like the micro DMA or the SRAM and the memory part, and keep all other peripherals in something else that is I explained in the last class, that is called the SMCLK, that is a sub main clock or subsystem clock. So how do you configure and how do you use all these kind of complicated clocking system for your microcontroller? So that is where I will begin. First, let us see that how many types of clocking is there. As I told you that day, that there are many type of clocking available. You can use many of them. One most important clocking system is the very low clock or VLO clock. VLO clock is nothing but a very simple RC oscillator with a very low accuracy, but you don't need accuracy when the microcontroller is in sleep mode. What you just need to do is, you just got to ensure that any kind of external interrupt can wake up the microcontroller, go to the interrupt service routine and do the job that it is supposed to do. So very low clock can be one of the clocking system of the auxiliary clock, right? So I'm sorry. So this very low clock or VLO clock can be used. So you see this block, this particular block over here. This block, as you can see, will select between two type of clocking systems, that is, one is VLO-CLK and the other is LFXT1-CLK, right? So which one of the two you will use will obviously depend on these two lines. So basically, if I explain, then this LFXT1SX, it basically stands for LFXT1S0 and LFXT1S1. These are 2 bits. These 2 squares, as you can see over here, these 2 squares below LFXT1SX, these squares are nothing but 2 bits, right? So any combination of bit, that is, say 10, as you can see over here, 10 in this trapezium, this 10, if you put a 1 and a 0 combination over here, then this trapezium allows the VLO-CLK to move out and then move into the divider, right? I hope you can understand. So putting LFXT1S0 as 1, that is this first bit, and LFXT1S0 as 0, which is the second bit, what you do is you basically allow VLO-CLK, that is very low clock, to move into the divider section of the auxiliary clock. Now what is the divisor for, or the divider for? Suppose if you want, for very low clock, this divider is of no use, let me tell you frankly. But for example, if you're using this auxiliary clock for your peripherals, And if you have a slow peripheral, like say a serial communication, or you have an ADC peripheral that is built inside your microcontroller, you will definitely want them to operate at a slower frequency than the microcontroller core, for the simple reason that if you're multitasking especially, or if you're doing some parallel job processing, then you will never want the ADC to overflow before the main CPU or the ALU comes back to the ADC and picks up the value. I hope you can understand. Suppose if you have two peripheral working parallelly, say if you are acquiring some value from the ADC channel 0, and if you are sending that value through the UART, that is the universal asynchronous receive transmit, that is the RS232 port, then you will obviously want both the peripherals, that is the ADC as well as the UART, to operate at a lower speed than the CPU core. Now ask me why. The reason is, if it so happens that both the peripherals are working at very high speed, then there may be a loss of value, because maybe the ADC has converted and is ready for conversion, or for the next conversion, but the CPU core hasn't been ready as yet, or is not ready to pick up the value from the ADC and send it to the serial peripheral. One option many of you guys might be thinking is, why not use the micro DMA? Okay, fine, micro DMA is good, you don't need the CPU intervention, but for basic students who are listening to this video for the first time, I would say leave aside micro DMA. I'm not considering micro DMA now. I'm just saying that in this case there's a chance that ADC value will be overwritten by the next read, right? So unless and until you control the ADC for the next conversion. But then again, if you make the ADC wait, then you might lose some value or vital analog data at the input channel of the ADC. So you have to divide the auxiliary clock by some value. Say divide by 1 means it is as same as that of what is coming from the clocking pulse, but the best option is to divide it by 2 or 4. That is, suppose if LFXT1 CLK is coming at say 16 megahertz, and if that is the frequency at which the core is running, then definitely you would want the peripherals to operate at 1/4 of it, that is 4 megahertz. So that is the reason why this divisor or the divider part is given. Now how much you want to divide with is again decided with this diva x. Well, this diva x is nothing but DIVA, that is divisor of auxiliary clock bit A, that x stands for bit 0 and bit 1. So if you make a combination of 0 0, that means it's divided, you are asking to divide it by 1. If you are using the combination of 0 1, you are saying divide it by 2. If you use the combination of 1 0, it means that you want to divide it by 4, and so on, right? Now for VLO-CLK, this divisor or the divider or the prescaler, as many microcontroller manufacturers say, is of no use, because you will never divide it, because the core is not working, you don't have any tension. But if you're selecting any other, here you can see there's one word, I'll tell you, there's one word called else. What is the meaning of the word else over here? The else means that any other combination of this particular bits, any other combination of these particular bits, say 0 0 or 0 1 or 1 1, will select the second option of the clock, that is LFXT1CLK. Now LFXT1CLK is a standard clock, that's a very high accurate clock, and it can operate from two sources. One is internally, or you can also use an external crystal. Well, internally, I'm sorry, not internally, internally with capacitors, but it can operate from several type of crystals. One is you can use a clock crystal, that is 32.768 kilohertz crystal that you can find in the RTC chips, or in the small clock. You'll find those small crystals in the clock. You can put that kind of a crystal over here. I'll just show you, just wait. I'm finding the tool I want. This is the one I'm saying. It's not this. This is the one I'm saying. I hope you can understand. I don't know how to select this. This is the one I'm saying. This one is X in and X out. So these are the two pins which are used for connecting the crystals, right? For the microcontroller that we will use, it will be pins P port 2.6 and 2.7. The beauty of the Texas Instrument microcontroller is that you can if you are not using any external crystal, and if you are using internal DCO or the internal DC controlled oscillator, then you don't have to bother about these two pins getting wasted, which is there in other microcontrollers. If you don't use a crystal, if you use an external clock source, or if you use internal clock source, in some microcontrollers what happens is that those two pins goes it goes unused. So here there is not an option. So for LFXT1 CLK, you can use either 32.768 kilohertz crystal, that is the low frequency crystal. Well, in that case, there are some special conditions that have to be made. Now, what are those special conditions that have to be made? Is that there is a particular bit in a register that is called XTS, right? So the XTS has to be set to 0. That is over here. This bit has to be 0. So if you're using a low frequency crystal, you just set XTS equals to 0, and the entire oscillation frequency will come to your LFXT1 CLK output. So if you are selecting this else option, then this 32.768 kilohertz crystal will generate a frequency, and that frequency or that clock pulse will be fed into the divider. Now your divider will come into use, and you can use it for dividing the frequency as you wish. Now, one thing you need to know, that is, if you're using a low frequency crystal like 32.768 kilohertz, then the starting capacitors which are used with the crystals, you don't have to use external starting capacitors. There are settings for using internal starting capacitors, and the values are selected. There are many values you can select. You can select 6 pf, 10 pf, 10 picofarad, 6 picofarad, 12 picofarad, and they are configurable using these two bits, that is X cap bit 0. The left square signifies bit 0, and the right square signifies bit 1. So for all these combinations, that is 0001, 1011 of these two bits of X cap X, will select various starting capacitors. So the starting capacitors are not required externally. But if you are using a high frequency mode, that is, if this crystal connected to X in and X out, right, if the crystal that is connected to X in and X out is a high frequency crystal, like for example 25 megahertz, say, which is the highest allowed frequency for 2553, the one in which we will be working, then you have to use an external crystal, right? Then x cap x, or the internal crystal, that is x cap bit 0 and x cap bit 1 will make no sense, because you need a higher value capacitor like 33 picofarad or maybe 47 picofarad, which is not possible to be made or constructed inside the die. So in that case you have to use an external crystal, and this XTS, just remember, which was 0 for the low frequency crystal, has to be made 1. So you have to make this value of XTS equals to 1. Okay, and suppose if you're using a crystal of say 20 megahertz, right? So your output will be 20 megahertz, and you use a crystal that is you use a capacitor of say 32 picofarad, but your XTS, if you put XTS equals to 0, then your oscillation will go to a fault mode. Okay, so now let us come to a very beautiful feature of MSP430, is the oscillator off. You know, this oscillator off, this is a nice thing. Why I am calling it a nice thing? Because sometimes it happens that, you know, the system that is running from an external crystal, it goes to a fault mode. The crystal is at fault, your system crashes, your oscillator goes to halt, your microcontroller goes to halt, and your entire product is just, you know, it is just not working. So when a product fails or a product goes dead, there are 1001 reasons why this might happen. But if you are able to know the reason, then it's a boon, right? So this oscillator off is nothing but a bit. This is a bit that keeps that can be used to switch off the oscillator. And if the oscillator off is not used, like if you are keeping the oscillator on and if still there is a fault, if still there is some fault in the clocking section, then that will generate or it will make a flag in the system register to go high, and that flag in turn will make a system interrupt if you enable the interrupt. That is called the oscillator fault interrupt, and that fault interrupt is a non-maskable interrupt. That is, you cannot stop that interrupt from happening. Once enabled, the processor will have to go to that to service that interrupt. It's a non-maskable. It is not a maskable interrupt. You can't stop the processor from going to that particular interrupt. So if the oscillator off is not used, that is, if OSC off equals to 1, this is a single bit. If this is equals to 1, which means that you have not switched off the oscillator, and if the system understands that there is some kind of fault, I'll explain how and where. If the system understands that there is some kind of fault with the clocking system, what it will do is it will simply latch the oscillator fault flag, that is OSC OFIFG flag, as far as I remember. I'll see it in the register, and that flag, once that flag is high, and if you interrupt and if you enable the oscillator fault interrupt, that is oscillator fault interrupt enable, if you make it equals to 1, then the processor will service the interrupt service routine. You can't stop it. Now in the interrupt service routine, it's up to you. You can write a code to log a data in the EEPROM or somewhere in the memory, or maybe, you know, send an SMS over the GPRS or whatever, that there is some kind of problem that is there in the crystal. And the beauty of the thing is, you will ask me, well, the core is not working, the oscillator is at fault, so how can I send the data to the EEPROM, or how can I send the data to the GPRS modem, or maybe to the Zigbee or to the Wi-Fi module? Now the beauty of MSP430 is, once it feels that the oscillator is at fault, it automatically switches to the DCO. That is the DC controlled oscillator, and that takes around 1 or 2 microseconds to settle. So within 1 or 2 microseconds, your core switches from LFXT1 CLK to the DCO, that is DC controlled oscillator, which is the internal oscillator, and log, and it will carry on working unless and until this particular problem is solved and this LFXT1 CLK starts working, and then you again reset the system, and then the system switches back to the external crystal. So that is something very important and very interesting feature. Here you can see one more bit, that is XT1 off, right? This is nothing but, if you don't need XT1 for some reason, you can keep it off to save power. Now I'm coming to XT2. XT2 is an optional, you can see, it is within the dotted brackets. It is within the dotted brackets because XT2 is an optional section. It is not present in all the microcontrollers of the X2XX family. So XT2, what you do is you connect an external crystal, and XT2, this XT2 off is again, if you want to keep the XT2 section off, then you set this bit equals to 1. But like we had XT1 off over here. So if you want to keep it off, then you put this bit equals to 1, otherwise it will keep on oscillating. And XT2S, this is controlling the frequency of the XT2 oscillator, and then the output comes to this particular section, minimum pulse filter. That is, it filters the pulse that is coming out of the XT2 block. And one interesting thing is that you can see is that connected only when XT2 is not present on the chip. So what it is saying is that this XT2 system, if it is not present on the chip, only then this particular line, how can I show you the line? Anyways, this arrow, what it is showing is the clock from this section, that is LFXT1 CLK and VLO-CLK, is also connected with XT2 output. You can see over here, here is VLO-CLK, here you have LFXT1 CLK, and this is the output, right? The output is connected also to the XT2 output. So this connection is done only when XT2 chip is not present. Otherwise, this connection is not done. This LFXT1 CLK or VLO-CLK output comes directly over here. This joining section is not there. It directly enters the 1-1 section. So selecting SELM as 1-1 will go to LFXT1 CLK or VLO-CLK as you select over here. Okay, I know I am going through very complicated theories. If in case you have any kind of question, please feel free to write me a mail, or if the question is very big or it is very complicated to write, you can always send me a video, or you can directly send me a voice record, so that I can listen to your question. But I need to know your feedback. Okay, so you can do it in the YouTube channel, you can do it in my website directly, as you wish, but you must understand the clocking. That is, this 1-1 is connected with 1-0 only when XT2 is not present. If XT2 is present, then what happens is this LFXT1 CLK directly goes to 1-1, XT2 goes to 1-0, and 0-0 and 0-1, they are connected with DCO. Okay, now one thing more, DCO is also connected to 1-0. That is not avoidable even if XT2 is not present. DCO, one thing you must realize is that DCO is present in all the three combinations, that is 00, 01 and 10, because MCLK is the main clock or the main system clock. MCLK must function whether your XT2 fails or XT1 fails or if VLO-CLK fails. That is the reason why DCO-CLK is connected to all the three inputs. But LFXT1 is exclusively connected to 1-1, right, when XT2 is present, and if XT2 is not present, then it is shorted with 1-0. So selecting 1-0 can either if you select 1-0, if you configure 1-0, if you select 1-0 over here as your clocking source for MCLK, then it can either come from DCO, it can I'm sorry, if you select 1-0, it can either come from your LFXT1 CLK, or it can also come from XT2, right? Now this particular section, that is the output of the LFXT1 CLK or XT2, goes to this part. Why it goes to this part, I will tell you later on, because when I go to the subsystem clock. So I hope this is now clear to you how XT2 functions. So XT2 input directly goes into 1-0, okay, and it's also connected to LFXT1 CLK, and it is also connected to one input of SLS. What is SLS? I'll tell you later on. Now once you have configured this particular bit, these two bits, that is, say if you select say 10, that is you are selecting say, let us presume that you don't have XT2. If you don't have XT2, then obviously 10 and 11 both will be connected to LFXT1 CLK. So if you have used LFXT1 CLK, okay, and if you have connected some crystal in the X in and X out, then that particular, say 20 megahertz, then 20 megahertz will come over here and it will come to both the inputs 10 and 11. So if you set SELM, this SELM, by now you must have understood that SELMX means that X stands for 0 and 1, or maybe more. That depends on the number of bits that is available here. It's a 2-bit configuration, so it will be SELM0 and SELM1. So according to these 2 bit combination, if you set as 10, then that clock, 20 megahertz clock, as I told you, which is coming from here, it will move into this divider. Now again you have a divider. You'll ask me why. The point is, sometimes you might not need the very high frequency of 20 megahertz to be used for your main system clock. Now the point is, again, why? Fine. Say your system is working at 20 megahertz, right? Now if I haven't covered that section, actually MSP430 has a wonderful frequency versus power supply profile. That is, the more frequency at which your core operates, the more power supply you need. Okay, so if your core is working at a lower frequency, you can make it work. You can operate it at even 3 volts or even I think 2.8 volts. Okay, so so the lower frequency you use, the lower power your CPU will consume, but usually people don't divide this. So DIVMX again means that DIVM0 is this first bit and DIVM1 is the second bit. Now here you have a very interesting feature which is called CPU off. What is CPU off? CPU off, it's like CPU off is kind of a it's a kind of a switching off technique. If you make CPU off, then the entire power consumption of the CPU goes to zero. But then what is the reason why you should make the CPU go to off state? The reason is, if you make CPU off equals to 1, then you can see that what it does is it simply cuts off the clocking. The 0 is connected with the clock source and 1 is connected with nothing, so it simply puts the clock thing off. It just doesn't clock the CPU. So what happens is, if the CPU doesn't get a clock, it doesn't operate, and if it doesn't operate, there are millions of transistors and millions of you can say capacitors and many many MOSFETs might be there, and MESFETs may be there, and many other electronic components that is actually doing your arithmetical logical work inside. So once they are all switched off or they are not working, your power consumption goes down. Now the point is, why do you want to make the power consumption go down or the CPU to be put off? For operations which are for devices or circuits that are operated by battery, they need this feature very much. You don't need the CPU to be running on a, we all love to write a program inside a infinite while loop and keep on waiting, keep on waiting, keep on waiting. Suppose if you have made a very simple thing, say a clock. How much time does it require for a clock to read the read the RTC and update the LCD or the LED or the or the output display device? Once in a second? Once in one? Have you ever imagined a crystal of even if you're using a 1 megahertz crystal, right? Then a 1 megahertz crystal, how many clock cycles is wasted for just reading the RTC and displaying it on the LED or LCD? So what the CPU off feature will do is it will keep the CPU off just when your timer module is on. So this is the beauty, this keeping CPU off doesn't mean that the timer module is also switched off. And I'll tell you the why TI has made all these kind of different clock architectures of ACLK, MCLK, SMCLK. So when you put the CPU off, MCLK goes to 0, that is the main system clock is off. So what will happen? What will happen is that the CPU goes to sleep mode, but the timer, which is keeping track of the time, you can power the timer from either ACLK or you can also power the timer from SMCLK. So when you power the timer module from SMCLK, that is not off, that is on. So the timer keeps on, the timer keeps on it keeps on counting the time, and when it becomes one second is complete, it will generate an internal interrupt. Okay, so just when the internal interrupt occurs, it will automatically clear this CPU off bit. So the CPU off bit is cleared and the 0 is selected. The main clock system powers on and the CPU does its work. It updates the LCD, and at the end of the routine you have to again put the CPU off equals to 1 to make it go to sleep. So in this way you can save the power of the system, you can save the power of the battery, and also you can extend the life of the microcontroller also to some extent. Okay, so this is all that you need to know about the main clock. Now let us come to the most important part, that is the DCO. Now as I told you, the microcontroller first starts off from DCO. After starting off from DCO, it first checks OFIFG flag, that is the oscillator fault flag. If the oscillator fault flag is there, then it and if you have the interrupt is enabled, then it will automatically go into the NMI and report that there is a fault with the oscillator. But we have to remember that whenever you power on an MSP430 microcontroller, the oscillator fall flag will obviously be 1. Okay, so if you are operating from DCO and your NMI is not enabled, and if your NMI is not enabled, so you don't have to bother. It can continue working on the DCO. But if you want to switch from DCO to LFXT1CLK or XT2, then there are some things that you need to do. I will explain it a bit later on. Now let me explain what is actually DCO. DCO is nothing but a DC controlled oscillator. You know, it is a DC. It has a DC generator that is basically, I would very simply put it as a clock pulse generator, right? It is a clock pulse generator that is controlled by DC voltage, and it will generate square wave pulses to proper accuracy. That is very much okay for you and your work to be done. But if you require extreme accuracy, then I would prefer go for external crystals, because DCO DCO can never give you the exact frequency that you want. There will be some kind of shifts from the frequency you want. The reason being that this DCO operates in step frequencies. Step frequencies means that there is maybe a frequency of 999.98 megahertz, and there may be the next frequency available is 99. I'm sorry. The first frequency is available is of 0.997 megahertz, and the next frequency available is say 1.056 megahertz. But you need 1 megahertz accurately. So in that case, it is very difficult to obtain the frequency from DCO. But in most of the general cases, you can very well use the DCO. You can save 2 pins, you can save external component costs, and use pin number 2.6 and 7 for any kind of use. GPIO, buttons, inputs, outputs, everything, right? So now what you see is you can use an external oscillator, that is ROSC, that is you can use an external oscillator into the DC generator, but that we hardly use. So what we will do is the DCO, that is a decor register, what it will do is the decor register, what it will do is it will select whether you are providing the external frequency from any timer, or you want the DC generator to operate from the VCC, that is a supply voltage. Well, usually we all use the VCC, and at least I have never used external oscillator in any of my projects. The next thing that you need to know is SCG0, right? The SCG0 will make the DC generator go off. Now the MSP430 to 2XX or any MSP430 platform, they have a beauty of, there's a beautiful thing that's called the low power mode. They have beautiful low power modes, I tell you. They have beautiful low power modes. There's LPM0, there's LPM1, there's LPM2, there's LPM3, there's LPM4, there's LPM 3.5 in some devices, higher end devices, 4XX series, they have LPM 4.5, and I think there is also LPM 5. So in step by step you can switch off sections of your controller, and you can drop the power consumption to nano amperes. It's almost nothing. So SCG0 is a bit which, when turned on, will switch off your DCO. If you don't need the DCO, of course, you can switch off the DCO, right? Now you will say, then how will my controller work? Well, again, if your main controller or the main processor is being routed from the DCO, and you have the ACLK connected to the peripheral and the timer, then the timer can very well operate from the ACLK, and the DCO can be switched off. Or even in cases where where you want to operate from external crystal like LFXT1CLK, then first the processor will start from DCO. That you cannot change, TI has fixed it. It starts operating from DCO, and then you have to write a bit of code to switch it to LFXT1 or XT2. But once it has switched to LFXT1 or XT2, you can put this SCG0 is equal to 1 and switch off the DCO part, because you don't need it anymore. You are operating from external crystal. But remember, if there is a fault with your crystal, the processor cannot switch back to DCO. Okay. Now there is a wonderful thing that I need to show you. That is this. Can you see these registers RCLX and DCOX? You know, they are nothing but they divide the DCO frequency into steps. How do they divide it into steps? I will show you. Look at this picture. Look at this picture. Now DCO has how many bits? 1, 2, 3. It has total of 8 bits, right? And your R cell has a total of, I think, 4 bits. So basically your register select R cell, this is called register select. R cell has 4 bits. What are they known as? R cell 0, R cell 1, R cell 2, R cell 3. So how many possible combinations of R cell can you have? You can have R cell 0, 0, 0, 0, then you can have 0, 0, 0, 1, you can have 0, 0, 1, 0, you can have 0, 0, 1, 1, right? You can have 0, 1, 0, 0, you can have 0, 1, 0, 1, and this will continue up till 1, 1, 1, 1. So if you count this, you will get a total of 16 combinations, that is from 0 to 15. And that is exactly why you can see that RCLX has 15, up to 15 you can go. Now DCO selects the range of the frequency and R cell selects the base of the frequency. That is, if you select R cell equals to 0, then your starting range would be 100 kilohertz. So if you select R cell equals to 0 and DCO equals to 0, well, also for DCO, I didn't explain the DCO part. Also for the DCO, what will happen? Just make the fonts a bit bigger. For the DCO, what will happen is, the DCO has 8 bits, so it's DCO 0, DCO 1, DCO 2, and so on up till DCO 7. So DCO will also have how many combinations? This DCO 8, DCO 0 to DCO 8 can be achieved by making the 3 bits of the DCO as 0, 0, 0 for DCO 0. So basically you have 3 bits for DCO, right? That is DCO 0 bit, DCO 1 bit, and DCO 2 bit. So if you use a combination of 0, 0, 0, 0, 0, not 0, rather it should be 0, 0, 0, this will select DCO 0, right? If you use a combination, say 0, 1, 0, this will select DCO 2. So say in this particular graph, right, in this particular graph, if we select, say, DCO 0, first. So that means you are located in the 100 kilohertz region or below that, right? Or you are located in the 1 megahertz region, or you are located in the 20 megahertz region. Now where do you want the DCO to operate? This 100 kilohertz region or 1 megahertz region or 20 megahertz region will be selected by R cell. So here you see the R cell, there are many values of R cell, right? It's R cell 0, R cell 1, R cell 2, R cell 3, R cell 4, R cell 5, R cell 6 till R cell 15. So if you say R cell is R cell 0 by writing the R cell bits as, we have already made DCO as 0 0 0, okay, which is equal to DCO 0. So once you make DCO 0, you select the frequency of 100 kilohertz or 1 megahertz or 20 megahertz, any one of the three. As you can see, because this is common area, you are under this particular area, okay. So now if you say that after this, if you put R cell RSEL bits as, it's a 4-bit system I told you, as 0 1 1 0, say. Now how much is 0 1 1 0? Can you tell me? It's 6. So what you do is you have R cell equals to 6. So R cell equals to 6 means that in which location are you located? So you have DCO 0 and R cell 6. So R cell 6 is located somewhere, this is R cell 7, so R cell 6 has to be located somewhere here, right? It has to be located somewhere here. So making DCO 0 and R cell 6 will make your processor run somewhere around, say, 900 kilohertz or 800 kilohertz. I hope you can understand. I don't have any much better system in my laptop to locate the area, but I hope you can understand. So this is why R cell is all about. I'll give you another example, then maybe it will be clear for you. Say for example, I said DCO, the 3 bits of DCO, I select it as 100. So how much is 100? It's 4. So when you select DCO as 4, you are located in this region, right? So when you're located in this region, now you have to select the R cell to define the frequency of operation of the DCO. So now you say, okay, I will select R cell as 7. So now what will happen is DCO 4 means it is this region, that is it can be it is almost near about 100 kilohertz, 1 megahertz and 20 megahertz, and R cell 7 is R cell 7 is over here. So R cell 7, this entire step, you must understand one thing, this entire step belongs to R cell 7. It is not that this is R cell 7, the before one, this part is R cell 6, this is R cell 5, this is R cell 4, this is R cell 3, R cell 2, R cell 1, R cell 0. No, this entire step belongs to R cell 7. The stepping is for DCO. So DCO 4 under R cell 7 goes to the middle position where the dotted line is. So your frequency of operation will be 1 megahertz. So that is how R cell and DCO bits combine to give you the perfect frequency at the output. So that is how your RCL bits and your DCO bits will be used to generate the frequency. There's something called the modulator. You don't have to worry about the modulator. You know, the modulator is used for synchronization of one particular frequency selected by the DCO and the next frequency that is there. That is, suppose if you select suppose if you select 1 megahertz and the next one is say around 1.01 megahertz, so it for every 32 cycles it will make a punch of the next frequency. This helps the clocking system run smooth, so that you don't have to bother much about. What you need to know is there's RCell and DCOX, and both of them, you know, they will be sent to this DCOCLK. This DCOCLK will be routed, I told you, to 0001, both of them. That is, if you want the MCLK to run from DCO, so 0001 will help you select the DCOCLK. And then DCOCLK also enters into the SELS, that is select. Here what is done is, you have like the main system clock, you also have the sub-main system clock. So for the sub-main system clock, you can have two source of frequencies or two source of clocking. One is the DCO, and as you can see from SELS, you can also select, if you select SELS equals to 0, then the DCO is sourced into the SMCLK. But if you select 1, then it will again go to the XT2, right? It will again go to the XT2. So XT2 is selected as a source of clock or clocking in case if you are selecting SELS equals to 1. And after that, there's a divisor. If you want to divide the DCO clock by, if you want to make it divisible by 2 or 4 or 8, and then after that there's a beautiful switching, that is SCG1. SCG1 will again, you know, enable and disable the sub-main clock. So if you want, so I hope you can understand one thing, that you know, if you put CPU off, if you put this thing off, SCG0 off, if you put SCG0 off, and if you put SCG1 off, then your SMCLK is also off, your DC generator is off, your CPU is off. So what happens is, your main clock goes to off, right? Your SMCLK goes to off, your main clock goes to off. You're only left with ACLK. Now for ACLK, so what happens is, your entire system is sleeping, only auxiliary clock is there, and the auxiliary clock can only you know, make it only acts like a heartbeat. Simply, it only acts like a heartbeat. It only allows the processor to assume to accept some external interrupts, wake up from sleep, and then it will turn on everything on, the DCO on, the LFXT1 on, XT2 on maybe, and then SCG0 on first to turn on the DCO. First it will turn on, CPU off will be made 0 for turning on the CPU clock, the main clock. SCG0 DC generator will be switched on, DCO will be on, then SCG1 will be made 0 in order to switch on the sub-main clock 1. So these are the facilities that is there in the particular processor, and This is mainly how you should, configure the clock oscillator part of your particular MSP430 microcontroller. There is nothing more than that. I'll just brief you once again. There are four type of clocks, that is VLO-CLK, LFXT1-CLK. LFXT1-CLK is operated from slow crystals, that is 32 kilohertz crystals, when you have to make XTS equals to 0. Or it can also be operated from high frequency crystals when you have to make XTS equals to 1. Or you can also use the XT2, which is a high frequency oscillator, or you can use the DCO. Now by default, the processor, when you switch on the system, the main clock, which actually runs the CPU, the main clock will always run from DCO. It will start from DCO. So after it starts from DCO, if you want to switch it to the LFXT1-CLK, there's a small part of the code that you have to write. It will go to LFXT1-CLK, and if it sees that there is some kind of problem and the oscillator fault flag is on, then it'll raise the oscillator fault flag, and if you have the oscillator fault interrupt enabled, it'll go to the NMI, non-maskable interrupt. It'll log the problem. That logging part, the program you have to write, it will never log automatically, and it has to clear the OF IFG flag, that is the oscillator fault flag. Otherwise, it'll keep on interrupting, and it'll again come back to DCO. So these are the main clock parts, and the DCO is the final part, where you have to first select the RCLX and the DCOX, that is the RCL bits. However, whichever frequency you want, you can select it from there. The beauty of MSP430 is, inside the ROM of the MSP430, all the frequency corresponding RCL and DCO values are loaded. So that I will explain when I will do a program to you. Suppose if you want to write suppose if you want to configure the DCO at 1 megahertz, you don't have to go to the graph and find out how much should be the value of DCO bits and how much should be the value of RCL bits. They are already there. You just select the right the syntax and the right values, and it is already included in the header file, so you don't have to worry about selecting them. So I guess that completes the clocking section of this particular thing. Now your work would be to go through the rest part of the datasheet. I have explained almost everything, right? Here is the part which I was discussing, that is the modulator. DCO modulator is that modulation part that I told you. It basically selects the upper DCO tap frequency and lower DC. Suppose if you have selected DCO 4, then the system by default also selects the DCO 5, and it punches both of them, and it creates a very stable frequency pattern. So that all that you will find over here, you don't need to bother. You can have you have a formula, a mixing formula, which generates the particular frequency that you need. And these are mainly very useful for systems which has a possibility of high frequency or electromagnetic interference in the area, like if you're using it in a high magnetic field or an electromagnetic application, or if your system needs EMI EMC compliance, then all these things is important for you. Otherwise, for simple applications, you don't have to bother. Now if you want to source, this is what I was telling you, if you want to source the main clock from the crystal, that is from XT2 or XT1CLK, then what you do is, after the power up condition, as they say, after the power up condition, the DCO CLK MCLK is automatically sourced from DCO CLK, that is the DCO will automatically clock the main clock. If required, MCLK may be sourced from LFXT1 and XT2. That is if you want, if your demand wants, because there's a limit of DCO above which it cannot go. So what you do is, you First is you turn on the crystal oscillator and select the appropriate mode. So you have to turn on LFXT1 CLK or XT2. I hope you remember there were there was a bit as XT2 off, so you have to remove that off, or LFXT1 off. You have to remove that off and turn on the particular clocking system which you want to use. Then you clear the OFIFG flag, right? That I will explain in the register part. Then you have to wait for at least 50 microseconds. This is because you have to give some time for the crystal to stabilize its oscillation. Okay, if you're using a 25 megahertz or 20 megahertz or 16 megahertz crystal, you must give some time for the crystal to stabilize on its oscillation. And then you check that if there is any kind of oscillator fault. If there is oscillator fault, then again you have to clear the oscillator fault and again wait for 15 microseconds, so that some crystals do take time to stabilize its oscillation. I have seen in my experience, crystals taking time up to 250 microseconds to stabilize its operation. This happens over the year if you have the device kept in a very remote location where it keeps on running day and night, so the crystal has a wear and tear. So every time you power on the device, this loop has to be run. So once the oscillator OFIFG, that is the oscillator fault flag, okay, it is the oscillator fault flag. Once it doesn't once the flag doesn't set, which means that the oscillator is working fine, your system will swap to the second mode. Once you swap to the second mode, or you swap to the LFXT1 or XT2, then you must remember that you have to you have to switch off the DCO. But I would say it is a very risky operation, because in future, if your DCO fails to operate, your external crystal fails, then your system goes to halt. Okay, here there is a assembly language. I'm sure nobody uses assembly language right now, although I'm a great fan of assembly language programming. So what they are saying is that you just put oscillator off flag, you clear the oscillator off flag, that is BIC means you clear the oscillator flag, right, in the system register, so that oscillator is on. Then you select the XTS as 1. This BSCTL1 is a register where this XTS is located. Okay, you make it in the high frequency mode, that is, you make XTS equals to 1. Then you select the particular frequency in which you want your crystal to operate, right? LFXT1, I showed you LFXT1 SX, that is S0 and S1, that selects the frequency in which your LFXT1 will operate. And then you clear the OFIFG flag, that is the oscillator fault flag. I told you, whenever you switch on the microcontroller, the oscillator fault flag will be equal to 1, that is by default, so you have to clear it, right? And then give some delay. This delay is given by this loop. This entire loop is for the delay. So this delay is for that 50 microsecond that we've seen over here. And then after that, you check again that if the OFIFG flag has been set or not, right? So if it is not 0, that is, if it is 1, this J and Z over here means that if jump not 0, which means that if the oscillator flag is not 0, that is, if it is still equals to 1, which signifies that the oscillator is having fault and it is not stabilized as yet. So you again jump back to the same loop, that you clear the oscillator fault and you wait, as I was telling you over here, test OFIFG and repeat steps 2 through 4. So once it becomes 0, then this condition fails, and then you can select the clocking source as SCLM1 and SCLM0. That is, SCLM1 plus SCLM0 means that SCLM bit 1 and bit 0 will be the combination. That is, SCLM will be equals to 1 0 combination 1 0 combination. If you go back to the page, you will see that SCLM 1 0 combination is the LFXT1 combination. So this is how you are going to select the particular clock system. Now one thing you must remember, sometimes it happens that your system is running in LFXT1 in DCO, and you are swapping to the LFXT1, like just now I showed you. Now here an interesting thing happens. As you can see that this is the DCO CLK, that is the DCO clock, which is a very high frequency, and your LFXT1 clock is very slow frequency. So, and your MCLK, which is the memory clock, is first sourced from DCO CLK, as you can see. But once you switch it to the LFXT1 CLK, it will not immediately follow the LFXT1 CLK. You can see that LFXT1 CLK falls after the arrow, after this curvy arrow. LFXT1 CLK falls, but my memory clock doesn't fall. It waits, and it waits until one complete cycle has been completed by LFXT1 CLK, right? And then it gets synchronized over here. So the synchronization occurs after one complete cycle has been completed by the LFXT1 CLK. It is not synchronized immediately. So these small things you don't need to know this, but these small things you must remember. Now these are the clock registers that you must know by heart. I'm very sorry to say, you must know by heart. You have to know the register bits which needs to be set and which is required for the perfect operation of the clock system. Now in this video I'm ending the video right now because for the reason that the register configuration can only be done after you go through this part of the chapter very clearly. Okay, so I'm giving you time. I will definitely upload the register configuration, but I will do it after some time, maybe today or tomorrow, but it will be done in a separate session, not with this, because the register values needs to be understood and configured. So till then, goodbye, have a nice time, and do go through all the details of this particular chapter 5, and for any queries you can always write me down to tujashu@tujashusworld.in, and please subscribe to my channel, my YouTube channel. You will find a link in my website tujashusworld.in. On the right hand side you can find subscribe to my channel. Over there you can click and you will have a subscribe button. Not many people have subscribed to my channel, I know, but if you subscribe I will be benefited. I will be able to give you more videos, more tutorials, more free projects. So please do subscribe. If you like my tutorial, please do subscribe to my channel. So thank you for watching, and best of luck. Happy coding.